I'm going to talk a little bit about the Waituna model that I developed back in 2001, and over the last 17 years it's blossomed into what I'm going to talk about today. Modelling Waituna Lagoon response to change, climate and management. Managing natural resources in a sustainable manner can be challenging. In addition to understanding how our environment functions and interacts under current conditions, we also have to consider future scenarios such as climate change and management criteria and how they may impact on the resilience of a resource. Models are useful for considering what-if scenarios. The purpose of this presentation is to demonstrate the power and flexibility of models to assist us in planning for resilience. Southland's Waituna Lagoon is situated 40 kilometres southeast of Invercargill, and it's regarded as one of New Zealand's best examples of a natural coastal lagoon. The surrounding wetland and its flora and fauna is of international significance, and its value for recreational, cultural and scientific values. The catchments that contribute to the lagoon are intensively farmed, and there are concerns that the health of the lagoon and its tributaries are under stress. Now, in a healthy state, the lagoon should be dominated by aquatic macrophytes such as rupia. To manage the lagoon to maintain healthy rupia, it's crucial that the lagoon is not open to the sea for extended periods, as saltwater can compromise the growing conditions. A closed lagoon, however, can compromise the drainage to the surrounding farmland. Historically, the drainage issues were addressed by manual opening of the lagoon by shovel. This has now progressed to the use of diggers and is overseen by the Lake Waituna Control Association since 1969. The diggers typically have more than 50 metres of barrier to cut through. The most effective openings occur in calm conditions with high lagoon levels. Since the introduction of the Resource Management Act in 1991, a consent has been required and opening can only take place when specified triggers are met. Current management allows the affected landowners to mechanically open the lagoon when it reaches a level of 2 metres above sea level during the winter and 2.2 metres from spring through to autumn. There's been much discussion on the effectiveness of various criteria and how these may impact on landowners and lagoon health. For example, as the lagoon level rises, the amount of light available to the rupia decreases, but at what level does this become an issue to its health? So maintaining lagoon health while satisfying landowners' drainage requirements is a complex situation, and future climate scenarios will only add to this complexity. A model was identified as a tool that could address this. So Environment Southland developed a water balance model that incorporates user-defined scenarios based on proposed management and forecast climate change. The model outputs for each scenario can be used to assess frequency and length of land inundation and the number of the days the lagoon is open to the sea. This information can be considered for future management of the lagoon. The water balance for the lagoon uses continuous flow data and rainfall data from the nearby Waihopa catchment, and continuous lagoon level and climate data from the east end of the lagoon. The lagoon storage has been established by LiDAR. Seepage through the beach barrier was estimated when inputs and outputs were equal during prolonged periods of stable lagoon levels, and a staged discharge relationship of lagoon level versus barrier seepage was established, and the resulting model was validated by comparing model daily values against actual measured lagoon values for the period 2012 to 2016, which is what you can see here. To model the natural variability of the lagoon closures, historic records of lagoon openings and closures since 1972 were tabulated, and the probability of the lagoon closing within a given month was estimated. So a Monte Carlo method was used by running the model 30 times using 39 years of Waihopa flow data and random closing events and openings for the desired criteria. The simulation was repeated for 6 different spring-autumn management criteria and for future projected rainfalls for Southland that have been developed by the Ministry for the Environment, and these have been based on projections from the Intergovernmental Panel for Climate Change. So the projections have 4 greenhouse gas trajectories that were adopted for use in climate modelling and research, and these are known as represented concentration pathways. So I'll just refer to these as pathways from this point on. So we have pathway 2.6, which is the blue line. That's a mitigation pathway that requires a removal of some of the present atmospheric CO2. So you can see the levels are slowly dropping off there. Pathway 4.5 and pathway 6 are stabilisation pathways, and then pathway 8.5, this is the worst case scenario. This is very high greenhouse gas concentrations by 2100 and beyond. So the Ministry of the Environment have taken these 4 pathways and modelled climate for different regions of New Zealand. And we've got some rainfall predictions for Southland for 2031 to 2050 and for 2100 to 2110. For this model simulation, I've used the 2031 to 2050 rainfall projections. I've chosen these because it's relatively soon and this will affect the current generation. And also the 2100 scenarios are going to be influenced by sea level rise, and that's beyond the scope of this model. So what we got here is a graph of mean seasonal rainfall percentage of normal against mean seasonal flow percentage of normal. And you can see that we have an increase in rainfall along the bottom there, highlighted in orange, of 5%, and that corresponds to an increase in flow of 5.2%. So essentially what we do, we take these increased flow percentages and apply them to the height graph that goes into the Lagoon model. So we have here the Lagoon model outputs. For interest's sake, I've included a model of the Lagoon left to its own devices. So the green line shows how the Lagoon would respond with current climate conditions and unopened to the sea. The blue line indicates baseline management with current climate conditions. So this is what we're experiencing now. You can see an opening that occurred at 2 metres in winter there and a random closing event in June of the following year. The orange line indicates baseline management with climate pathway 4.5. You can see a couple of spring-autumn openings at 2.2 metres. So this is just a small snapshot of 1170 years of data generated from a single model run. All this data is collated into tables showing the number of days the lagoon was above a user-defined level and how many days it was open and closed. For each of the climate change scenarios, we have a simple summary. So modelled lagoon levels for the 4 climate pathways using baseline management showed that the annual average number of days above 2 metres increased from 2.7 under current climate to 4 for pathway 4.5. The maximum number of days above 2 metres increased from 23.1 to 53.1 days for pathway 2.6. So these results indicate that land use will be affected by changes in climate. An interesting point to note is that pathway 8.5, which is for continued growth, has lower maximum number of days above 2 metres. Now this pathway is predicted to have the highest spring and summer rainfall and higher river flow than the other pathways, so a decrease in the number of days above 2 metres seems to contradict this. The explanation is that this increase in river flow means that during the spring-autumn period, the lagoon is more likely to reach that 2.2 metre opening criteria, and so it gets open and does not spend as much time sitting in that narrow range between 2 metres and 2.2 metres. Another observation from the results was that for all the climate change pathways, there are projected increases in the number of spring and autumn openings at 2.2 metres. Under current climate conditions, this has an estimated average of 0.16 openings per year, but under pathway 4.5 that could more than double to 0.36 openings per year. The winter openings, however, remain generally unaffected, with just minor increases from 1.23 openings per year to 1.45 for pathway 4.5. The average number of days the lagoon was open to sea increased from 118.6 days to 133.3 for pathway 2.6. This was an interesting result, as pathway 2.6 is a mitigation pathway and has lower winter, spring and summer rainfall than the other pathways. It does, however, have higher projected autumn rainfall, which results in a 4.6% increase in autumn river flow. So this could mean that the lagoon's more likely to reach the 2.2 metre trigger level in autumn rather than the 2 metre trigger level in winter, and this gives it an extra few months of opening in some events. Although these can be rare, they're enough to increase the average, and the upper quartile increases quite a bit by 42 days to 199 days. The results from the model demonstrate its usefulness to Environment Southland and its stakeholders. The ability to model inputs into the lagoon based on climate scenarios and management criteria enables us to take user-defined criteria and model lagoon level and the resulting days of inundation of land and also exposure to the lagoon to salt water. The model is also used for short-term predictions. Global weather model data is fed into the Lagoon model to enable us to predict if trigger levels may be reached by approaching weather events. We can also estimate how long it will take the Lagoon to drop below trigger levels. So, to reiterate the opening points, managing resources in a sustainable manner can be challenging. We need to consider change from the current situation to plan for resilience. And models are a useful tool for assessment of hypothetical criteria, and they help us to plan for resilience to climate change and resilience to management criteria.